Hold a grain of sand at arm's length. The James Webb telescope pointed at a sliver of sky that size, and in just 12.5 hours revealed thousands of galaxies, one from barely 290 million years after the Big Bang. That sliver covers less than 1% of the sky. The true scale of the universe Webb has uncovered is something no human mind was designed to hold. Infrared light holds secrets that visible light cannot reveal. Most of the earliest galaxies are so far away that their light has been stretched by the expanding universe, shifting from ultraviolet and visible into the infrared by the time it reaches us. The James Webb Space Telescope was built to catch this ancient glow. Its primary mirror, spanning 6.5 meters across, collects even the faintest whispers of light, signals so dim that no previous telescope could hope to detect them. At the heart of Webb's discovery engine are two instruments, NIRCam, the near-infrared camera, and MIRI, the mid-infrared instrument. Together they can spot galaxies hidden behind cosmic dust, as well as those whose light has journeyed across nearly all of cosmic time. Webb's sensitivity is staggering, about 100 times fainter than what Hubble could see in the same amount of time. This leap comes from both the size of Webb's mirror and the extreme cold of its design, with optics and detectors kept at temperatures near absolute zero. Only in such cold can the telescope distinguish the faint heat from distant galaxies against the background of space itself. By opening this infrared window, Webb reveals a universe far older, richer, and more crowded than anyone could have imagined. Each faint dot, once invisible, now tells a story from the dawn of time. The first deep field from the James Webb Space Telescope, centered on the galaxy cluster SMACS 0723, is more than a photograph. It is direct evidence of Webb's reach. This single image was built from 12.5 hours of exposure time, a stretch of patient observation that allowed the telescope to gather light from objects so faint they had never been seen before. In a patch of sky no larger than a grain of sand held at arm's length, thousands of galaxies crowd the frame. Each faint smudge is not a star, but an entire galaxy, containing billions of suns and perhaps countless worlds. Some of these galaxies are seen as they were over 13 billion years ago, their light magnified and warped by the gravity of the foreground cluster. This phenomenon, called gravitational lensing, acts like a natural cosmic telescope, bending and amplifying the light from galaxies even farther behind. The result is a layered portrait of the universe, with foreground and background galaxies stacked together in one astonishing view. The colors, though striking, are not what the human eye would see. They are carefully chosen to translate invisible infrared data into a form we can understand. Far from being artificial, this false color processing is a bridge between raw data and human perception, revealing structures and histories that would otherwise remain hidden. The image is a map of the universe's crowded past, captured in a single, impossibly small window onto the sky. A single galaxy, JWST 14-0, stands out as a turning point in our search for the universe's origins. For decades, astronomers relied on candidates, objects that looked promising but lacked proof. With Webb's NIR-SPEC instrument, that uncertainty faded. By capturing the faint signature of JWST 14-0 and measuring its redshift at 14.32, scientists locked in its place in cosmic history. This galaxy's light began its journey 290 million years after the Big Bang, when the universe was only about 2% of its current age. Before this, the record belonged to GNZ 11, a galaxy found with Hubble at a redshift of 10.6. Webb's confirmation of JWST 14-0 didn't just push the boundary further, it transformed a distant candidate into a measured reality. In that moment, the abstract vastness of the early universe became something we could point to, measure, and begin to understand. Earth is a world that feels familiar, yet its size is already beyond daily experience. The planet's diameter stretches 12,742 kilometers from side to side, a distance that would take a commercial jet over 15 hours to cross non-stop. But this is only the first rung. The Moon orbits at about 384,400 kilometers away, nearly 30 times farther than the circumference of Earth itself. For centuries, this gulf defined the edge of human imagination. Then the scale leapt again. The average distance between Earth and the Sun, one astronomical unit, measures 149.6 million kilometers. That is more than 350 times the distance to the Moon, a span so great that light itself takes over 8 minutes to cross it. Even our most ambitious machines barely dent these numbers. Voyager 1, launched in 1977, has traveled for more than 4 decades and now drifts about 22 billion kilometers from home. Yet, on the cosmic map, this is still the solar system's backyard. Imagine driving a car at highway speed, 100 kilometers per hour, without stopping, day and night. After a lifetime, you would still be short of the Moon. At that pace, reaching even the nearest star would take over 50 million years. Ordinary intuition collapses long before we reach the true scales that the universe demands. Beyond the reach of our Sun's influence, the numbers begin to stagger. The closest star system, Proxima Centauri, sits 4.246 light-years away. For comparison, every planet and probe humanity has ever launched remains trapped in a bubble so small that from Proxima's distance, even the entire solar system would be invisible, lost in the glare of the Sun. 4 light-years is 40 trillion kilometers, a gulf so wide that even light, racing at 300,000 kilometers per second, takes more than 4 years to cross it. Yet this first leap into interstellar space is only the beginning. The Milky Way, our home galaxy, stretches roughly 100,000 light-years from end to end. If Proxima Centauri were a pebble just outside your door, the Milky Way would be a continent. To grasp the scale, imagine shrinking the galaxy to the size of a dinner plate. On that plate, the entire solar system would be smaller than a single atom, and the distance to Proxima Centauri would vanish into nothingness. Every human memory, every story, every achievement would fit into a space so small it disappears entirely at this scale. The mind strains to hold numbers like these, but the reality is simple. Even the nearest star is unimaginably remote, and the galaxy itself is a realm so vast that our existence becomes almost invisible within it. The universe, as revealed by Webb, is not just large. It is overwhelmingly, humblingly immense. Beyond the Milky Way, the scale of cosmic structures rises by orders of magnitude. The nearest large spiral galaxy, Andromeda, lies about 2.5 million light-years from us, a gulf so vast that even light traveling at 300,000 kilometers per second needs 2.5 million years to bridge it. Together with the Milky Way and dozens of smaller galaxies, Andromeda forms part of the Local Group, a gravitational family spanning nearly 10 million light-years across. Yet the Local Group itself is just a single thread in a much larger tapestry. 50 million light-years away, the Virgo cluster anchors a gathering of more than 1,000 galaxies, its mass binding the motions of entire galactic swarms. Zooming out further, the universe reveals a structure even grander, the filaments of the cosmic web. These threads stretch hundreds of millions of light-years, connecting clusters and groups into a network that traces the distribution of dark matter and the echo of the Big Bang. The largest structures ever observed, these filaments define the architecture of the cosmos on the broadest scales. At the utmost edge of what we can see lies the observable universe, a sphere with a radius of about 46.5 billion light-years. This boundary is not a wall, but a horizon defined by the age and expansion of the universe itself. Beyond it, light has not had enough time to reach us since the beginning of cosmic history. In every direction, the universe extends farther than imagination can comfortably hold, And Webb's discoveries remind us that our familiar world is a tiny island in a sea whose shores remain forever out of reach. Redshift is the measure of how much the wavelength of light has been stretched as the universe expands. When astronomers say a distant object has a high redshift, they mean its light has traveled through an ever-growing cosmos, and its original color has shifted toward the red end of the spectrum. Look back, time is the duration that light has been traveling before it reaches us. So when we observe something billions of light years away, we are seeing it as it was billions of years ago. This is not just a trick of perspective. It is a direct line into the past. The farther we look, the further back in time we peer. Webb's ability to detect infrared light is the key. As the universe expands, visible and ultraviolet light from ancient galaxies stretches into the infrared. Only a telescope tuned to these longer wavelengths can catch such ancient signals. Through Webb, distance and time become inseparable. Every faint, red-shifted glow is a message from an earlier chapter of cosmic history. Astronomical images from Webb are more than breathtaking views. They are precise measurements, built from carefully calibrated data. Each pixel contains information that scientists analyze using cosmology, the science that connects what we see to the distances and ages of objects across the universe. High redshift galaxies, those whose light has been stretched to the extreme by cosmic expansion, serve as records from the universe's earliest moments. By studying them, researchers reconstruct the timeline of cosmic history. The James Webb Space Telescope doesn't discard what was known before. Instead, it sharpens the picture, confirming and refining our understanding. Every new observation adds detail to a model that remains under constant scrutiny and revision. Right now, Webb's images reveal galaxies born over 13 billion years ago, proof that the universe is vaster and older than we ever imagined. Each discovery redefines our sense of place. Amid cosmic immensity, our smallness isn't insignificance. It's an invitation to wonder. What will we dare to seek next?